Okay. Okay. So I just want to kind of start off with ring theory and maybe reminding you of a few terms. Okay, the idea is like with groups, we had this multiplication. We could do some different things with it, like we could think of a group acting on a set or something like that, or other things. You know, and we did all the usual algebra stuff, which is to talk about subgroups and homomorphisms and all that stuff. Okay. And now we want to do the same kind of thing, except for rings. So informally, you know, rings just have addition and multiplication instead of just one or the other, you know, working together. Okay, and we want to do, you know, basically, we want to figure out what's going on with rings. An example of a ring is the integers with just, I guess I'll say standard addition and multiplication. Okay, what's another example? The integers mod n with addition, multiplication, both mod n. So sometimes a group is also a ring, you know. That's another example. N by m matrices over a field. Oh, sorry, I should say n by n matrices over a field. You can add two matrices and you can multiply two matrices together, you know, and they satisfy some nice properties or something. You also have the ring of polynomials. Polynomials with coefficients in a field K, whatever that means. Of course, an example of a ring is just any field, K, some field. So like real numbers, complex numbers, rational numbers, Z mod PZ, etc. Okay, I don't really know how to describe it, but somehow the feeling of then how groups are. So even though the definitions like seem quite similar to the same definitions for groups, the things that happen are not the same. Okay. So let me just write down the definition of a ring. basically we just wanted to have addition and multiplication, and we want to do all the normal things we're able to do, like the distributive law and all that stuff. Okay, so we have a definition. A ring is a triple R plus times, where plus and times are binary operations. Plus times. And that satisfy a bunch of different properties. Basically all the rules you want to have when you do algebra. So there exists 0 in R. 0 plus x equals x plus 0 equals x for all x. 2. Every x has a negative. Okay. The addition is commutative or abelian. And of course, addition is associative. Okay. Then the rest of the properties are involving multiplication. Okay. There exists 1 such that 1 times x equals x times 1 equals x for all x. 6. For all x, y, and z. We have the associative law. Then we have distributive laws. Okay, that's it. And then that's the definition of what a ring is. Basically this, oh, did I tell you? Oh yeah, R is a set. Okay. Then if xy equals yx for all y and x, then R is called commutative. Okay. So a ring can be commutative. Our main focus is commutative rings. At least for now, well, in this class. Of course, non-commutative rings are like very interesting and can do a lot with them. But if we just focus on commutative rings, it just makes a lot of the definitions easier to state. So that will just simplify our lives if we focus on that. Okay, so it's coming up next week. What we want to do is just take a quick review of a few things. I'll try and write down a table for you so that it's not like they're kind of like familiar concepts. So for groups, we have some things. For rings, we have some things. And for vector spaces, we have some things. Okay, so we might have like subgroups. For rings, we might have subrings. For groups, we might have normal subgroups. For rings, we don't have normal subgroups, we have ideals. Already, it's a little bit different. For groups, we might have homomorphisms. Well, for rings, we just have, well, we call them homomorphisms still, but they're just ring homomorphisms. Okay. You know, and we have isomorphism theorems for both. Oh yeah, we have quotient groups. Well, we also have quotient rings. And then we have the isomorphism theorems. Well, we also have the isomorphism theorems for rings, but they're just slightly different. Well, because rings are different than groups. Okay. I'll just remind you what are the things for vector spaces. Well, you have vector subspaces. You don't have a separate thing for normal, you just have subspaces. You have linear transformations, are the homomorphisms. Okay, you do have like quotient subspace, quotient space, kind of. And then instead of the isomorphism theorems, what you have is kind of like the rank nullity theorem, which is actually like a lot stronger than the isomorphism theorems. And then you have like a lot more concepts that like correspond. Like you can look at groups generated, like generators for the groups. Well, you can look at generators for rings, and lots of things correspond. Okay, so I'll just put dots. Okay. Okay, so there's one where I want to stop for this week, because I have this other, it's just a, oh, I sent it to the wrong thing. Yeah, so at this link, it's just a questionnaire. You can kind of fill it out and let me know what was making sense and what was not working. If the questionnaire is not working for you, you can just tell me that too, that's fine. Okay. Today. So you know, thanks for watching. I will see you guys on Monday. And have a good weekend.